Yeah, so Anna in Artak, it would be good if you switch on the camera because if if I feel like I explain to myself, I forget to say half of the things. Okay. So let us start. Can you read it? It's okay. It's a bit difficult, I'm afraid. So I have my best marker is this one. So I will write with black. It should be a little bit easier to read on the recording or on the stream. Okay, so what's planned for today? So there is only one task left. It's programming task. Well, a few programming tasks. And the first task will be about vertex cover problem. So I didn't set up the grader yet because everyone asks me to do it in C++, but I was very busy and so I need to learn this. And so I hope to do it in the next few days. So, and programming exercise will be to solve a vertex cover problem, the first one. And for this, it is advisable to use techniques from linear program, from parameterized complexity. So kernel construction and branching. And in this lecture, we will repeat the things that we learned previous time in the lecture. So we had two lectures about parameterized complexity. So one introduction and second lower bounds. But for programming exercise, we don't need. Lower bounds are less important. So you can forget about lower bounds. And so let us remember what is parameterized, what is a parameterized problem. So before we spoke about decision problems most of the times. So that means that the input was a string, and we have to say whether string is in a given set, yes or no. And so, for example, a graph with n nodes could be represented by a string of length approximately n squared. So n choose 2 to be precise. And then we wanted to know whether graph has certain property or not. Has it Hamiltonian cycle, yes or no? Okay. So now we want to know whether it has a vertex cover of certain size or a clique of certain size. So parameterized problem, it is a subset. Okay, let's do the whole picture again. So let us just spend 10 minutes on philosophy. So what we said before, we had a bunch of problems, and most problems in practice, they lie on some line. It's a bit, so here we have easy problems, and here the difficult ones. And with lengths of computational complexity. So in algorithm class, you have very fine lengths. You will really care if something takes n squared or n cubed or so forth time. In this course, we want to know difference between polynomial, exponential, or like with bigger steps. We don't care so much. And so for us, the easy problems, they are problems that are polynomial time solvable. They're the easiest ones. And then in practice, you have a lot of optimization problems in industry. And then there are decision variants. So in the first lecture, we explained that if we can solve decision problems, we can solve optimization problems. And so the hardest one in practice, they are NP complete. So there are a bunch of problems in crypto, and they are commonly believed to be in between P and NP complete. So there are problems in NP. So like factorization, if I give you a product of two prime numbers, can you find the first factor, or say whether there is a factor that is relatively small? So this small factor problem is believed to be NP intermediate. If it were NP complete, then it would mean NP equals co-NP. It would have huge consequences. But okay, we also discussed about harder problems. There were p-space complete problems, and they come from interaction. So if you play against opponent, so if you write program that plays Go or chess, then well, and there's some of these variants, they are p-space complete, but most are even harder, like X complete or X space complete. So we know that there are infinitely many difficulties between P and NP and between all these classes, but in practice, so except for crypto, problems are usually in precisely one of these spots. And here, in practice, the line is more complicated. For example, problems in NPN that are like SAT and complement of SAT, they're incomparable. They don't reduce. So here I ordered problems according to polytime reduction. And so then in the end of the course, we understood that all these problems like clique, vertex cover, dominating set, they are the easy variants of real-world problems. And they are all NP complete, and we zoomed in these problems. So we zoomed in and we said that some of these problems, they are fixed parameter tractable. So here so here I look to those problems that are still. So if problem is NP complete, we know there is no algorithm that always works on all inputs and is guaranteed to run in polynomial time. So it works. So for the optimization version, we get exact answers. It runs in polynomial time and it works for all inputs. And so we know if problem is NP complete, then we need to relax the requirements. And then we studied optimization problems. And now the plan is to have a trade-off. Let's say either not look to all possible inputs, but special inputs that for which the parameter is small. And allow more time and have some trade-off. So, for example, I will soon. So, but then we said that not all problems. So the requirement here is that there is an algorithm that on input n runs. So given n and a parameter k, input length n and a parameter k, we want an algorithm running in time f to the power k times n to the power of 1. So polynomial in n if we fix k. But moreover, when we fix k, the dependence is in the linear constant, not in the exponent. And so fix an FPT algorithm is that if we give a graph with n nodes, and we, for example, agree that the degree is at most k, then algorithm should run in polynomial time. But here the dependence of k can be big. So this is FPT algorithm. And we understood that for a vertex cover problem, it was a good problem. We could find the search algorithm. So k was the size of the vertex cover. So if we get the graph and we need to find a small vertex cover, we can do it efficiently, kind of efficiently. We can do it in time 2 to the power k, n to the power something like n squared. So we can do it in this time. So it was a good problem. But we learned that under exponential time, under certain hypotheses, clique is not a good problem. That we suspect that clique cannot be solved in such a problem. So the best algorithm is basically n to the power k runtime. So you can like have k 0.782. So there are exact advanced papers that have something like this. I don't remember the coefficient. Something like this is state of the art. But we have n in the exponent here. So this is much harder than vertex cover. And so, and we also could understand this under parameterized reductions. So we said that the clique problem was complete. And so here we have the clique problem with size as parameter was W1 complete. And then there was also a W2 complete problem, which was a dominating set problem. Oh, dominating set. So they're the problems that are, when we see that our problem is of this form, in W1 complete like click, we really need to go back to our problem and find a way to look to the data and hope to find a new parameter, or really revise our problem, or tell the bus we cannot do brute force searches. Unless the parameters are really, really slow. Okay. Oh, yes, please come. So I was just doing recap. So if you remember anything, okay. So now we are already with 5 people. So there's great improvement, and 2 people in the class. Okay, you didn't miss anything because I was explaining the philosophical thing. So, but here, not all problems that are fixed parameter tractable are in NP. So here I mean problems that are both in NP and FPT, of course. So they're the relevant ones. Okay, so now our task is given a problem. So in the lecture, I will give better algorithm for vertex cover for the programming exercise. You don't need to use everything. Actually, I will expand the test set so that and give you some extra functions. So I will upgrade compared to last year the exercise a bit. Okay, but I will later tell you what you should not use from the techniques. Okay, so and then our plan, and in the end I will speak about dominating set. So I will say that when we use the degree as parameter, maximal degree of the graph, then dominating set is parameter tractable. So it's W complete if the size is the parameter of the dominating set. So here for the clique, we also know that if the parameter is both the size of the clique and the maximal degree, then it's FPT. Let me repeat this because it's a nice way to. So let me ask you a question. Do you remember that if I give you a graph with small maximal degree and I ask you, does it have a clique of size at most k? So D is the maximal degree. Does it have a clique of size at most k? So then there is a good algorithm for this if this maximal degree is not too big. So you remember this algorithm. It was the very first example of FPT algorithm. So while you're thinking, let us recap. So what would be a very stupid way to do brute force to find a clique? And I mean, just the general algorithm is, so to find clique of size k, you try all subsets of size k in a graph. And so if the input, so graph, so let n equal be the number of nodes. And then the question, exist clique of size, and also graph and the integer k are good. So you all remember what is clique, right? So just to be completely sure. And so what is maximal size of clique in this graph? By the way, can you see this? Yeah, okay, thank you. Because the marker is already going bad. I have many other black markers, but they are thin. This is so this is not good. I got a new one, and I can be. Okay, maybe this is maybe this is good. Okay, so what's maximal size of a clique in this graph? 3. Okay, just double check that at least the problem is still clear. And so if we do brute force search, we could check all subsets of size k. And so if there are n nodes, then we have n choose k things we have to check. And this is approximate. So if k is not too big, then this is nicely approximated by n to the power k. Yes. So if k is equal to log n, it's already more than polynomial. But we can do better. So my question again. So if the parameter is both is d, and this is just maximum degree of node in graph. So what would be a better algorithm if we know that the degree is small, relatively small? So so there was algorithm that runs in time 2 to the power d poly n. So do you remember? So we have to find a clique of size k. What do we know if k is bigger than the max degree d? Let's say 2 bigger. Well, yeah. So what if d is d is bigger than k plus 2? D is maximal degree, then we know answer is?
There's no.
Yeah, no. Because in a clique, every node has a clique of size k, every node has k minus 1 neighbors. So then we say no. Okay, and now what's the better algorithm? So we want to brute force search. So what's the algorithm that gives this running time?
I remember that we can
Yeah. Okay, so we know that if a node belongs to a clique, then what do we know about
every node in this clique has the same?
Yeah, must be in the neighbor or neighborhood of this. It must every node of the clique must be a neighbor of this node. Yeah, yeah. So what we do? What's the algorithm?
I don't remember, but we can search for the nodes that have at least k.
Yeah. We pick any node with at least k neighbors.
And then
About k minus 1 neighbors.
yeah, and then just see all the subsets that this node.
Yeah, exactly. Yeah. So we pick any node and then we try. We only look to the neighbors of this node and we try all the subsets. And so if our parameter in the problem is this d degree, then we have an algorithm that runs some function of the parameter times polynomial in the input size. So that's the definition of FPT. And so formal definition. So formal definition. So a problem and so problem parameterized problem is a subset not of strings but parameter times strings. Parameter times strings. So sigma is some alphabet, usually binary alphabet, but can be any alphabet. And so we say that P is in FPT if there exists computable function F and constant C well, computable function, constant C, and algorithm. That on input kx decides the answer, says whether kx is in P. And now the important part, the runtime. It's time. And then here we have f of k times n to the power c. Okay, maybe I should say big O. It's not really needed just for the case that n is equal to 0. I put big O. Big O says we start from large n because, okay, but it's not really needed. No, okay. For 0, we can just in 0 steps say the answer and hard code. So, okay, let's not do stupid. So that should be the runtime. And so here, this problem, so the parameter is d, and then the input is a graph and some number k. It's an FPT because of this one. Okay, so now next step, let's prove that vertex cover problem is FPT. So do you remember how we did this last time? So there was some clever idea. We used the branching algorithm. So we know that if we pick any edge, so remember what is vertex cover? So
Any edge.
it's set of nodes such that every edge hits at least one node in the set. So what is minimal size of vertex cover here?
3.
3, yes. So can you tell me which nodes? So for example, this node and which else?
The right, the left.
Bottom, yeah. And now is everyone covered? Ah, sorry, the two, yeah.
We need at least one.
No, yeah, you're right. So this edge is not covered now. So we need to add either this one or this one. And it's minimal size of vertex cover. Yes. Okay. So here, so question, exists vertex cover of size at most k. And the parameter is k. So this is called natural parameter. So when we ask, does there exist set of size at most k, then the size is the natural parameter. This k is the natural parameter. Okay, and so brute force and choose k, which is basically n to the power k, which is very bad. And we can do it in 2 to the power k n to the power of 1. So what's the idea? So we will look like we did here at this edge. And we know one of the endpoints must be in the set. And so we create 2 new problems. So we will think that either this is in the set and then recurs. So we will remove the node and the edges on it and recurs, or we think that this node is in the set and then we remove this node, decrease k by 1 and recurs. So let me draw the picture, but it's needed. So do you remember? Okay, let's do it quickly.
It's not about this yeah, BFS. So you choose one, no?
Yeah, then you choose neighbor. So here we pick just any edge. So let me draw, yeah. But okay, in kind of search tree, then you can depth first search if you think about search tree. So you can choose edge It's either which one. So let us pick this edge. And then we have two branches. So either we will say that this is in the solution, or we will say that this one is in the solution. If this is in the solution, it means that we are good for these three edges. So we just draw the graph that is left. So this, yes. So this graph is left. And otherwise, we remove this node. So what we have left is this one, this graph. So here we want, for example, we want to know if this has a vertex cover of size 3. So then the input is graph and number 3. And here will be this graph and number 2. And here we will also number 2. And now we recurse. So here we can, we again pick an edge, for example, this edge. And we remove left node or right node. So that's all vertex cover algorithms. They are branching algorithms. But, okay, and here is something interesting in this graph because it's path. And for path, we actually don't need to recurse. So we could do the same, take an edge, remove left node or right, and the other node, and then recurse. But we can make a better algorithm. When we see all nodes have degree 2, we can directly tell the answer. So what is minimal vertex cover of this graph? Yeah. So it's number of nodes divided by 2 and rounded down. If you have path, so you take, and so here indeed you have 2, and so this is yes. And if one of the branches say yes, then our search is successful. So let us say 2. If we start with 2, then we recurse with 1 here, and then this will be no branch. So it means we have to continue to the next branch. So here, and then we can again choose some edge, say this one, remove this node. And then we lose because this edge is not covered. Or we choose this node and we lose also, this edge is not branched. And so here we have 2 branches. And so our algorithm works in this time. And so this is in the lecture notes of in December, you can read in detail, I wrote the algorithm. I will not write it down. You're clever enough, if we put any graph in K, you understand how the tree will look like. It will be binary tree. And the depth will be, well, K decreases by 1 at each level. And when it's 0, we just have to check that there are no edges left. If it's 0 nodes, we cannot cover any edge, of course. So if edges left, we say no. If no edges are left, we say yes. And so here we have recursive algorithm. So number of nodes in the tree, recursion tree, is 2 to the power k minus 1. And so in this level, we have 1, 2, and then we have k minus 1 levels. No, k levels, but or k plus 1. And anyway, order 2 to the power k. Doesn't matter, the constant, yeah. So number of work in every node is polynomial. So we have this runtime. So now we understand vertex cover, it's good problem. Clique problem, bad problem. If we believe had exponential time hypothesis. And so this we explained in last lecture in December.
Sorry, why do we only choose like 2 branches? Why?
So if we look at one edge, so you can make better algorithm. I will quickly explain. But if we look to one edge, so this is our deal. Let's look to an edge we know that if one node is not in the edge, the other node must be in the edge. And so we have two cases. Either this is in the vertex cover or this is in the vertex cover.
Oh, okay.
And then we decide, okay, so imagine that we believe this is in the vertex cover, then we go to this branch or the other branch, this branch. And then, okay. So, but then in December, we said that there was better algorithm, 1.4645. I forgot 454, it doesn't matter. So something like very close to this. To the power k times n to the power of 1. And so there was idea to have more branches. Was the idea. So what is now idea? Instead of looking at edges, let's look at the nodes. So we say that either the node itself should be in the vertex cover or all of its neighbors should be in the vertex cover. This was the idea. So now we have more branches. And so we take a node and we say either this node is in the vertex cover, but if this is not in the vertex cover, then all its online branches need to be covered. So this, and this node must be in the vertex cover. And so we have two branches. In one branch, we have the graph. Well, to say I should have deleted that. And so, and we decrease by 1, but in the other branch, k decreases by much more. Okay. Let's say that we start at 5, then we are in 4. But in the other branch, we put 3 nodes in the vertex cover. And so we have something with 2. So we put 3 nodes, only 2 are left, and they are isolated. So no edges, and so here we say yes. And in the other branch, we need to work more. And so this is the idea of the algorithm. So we will pick a node with very large degree, and then we will decrease k by 1. But if this branch doesn't work, we have very little work left. And this is true for every branch. We always have, so we have a tree, and always one branch is much smaller than the other branch. And then we get much better runtime.
Yeah, but there, you told us about greedy vertex cover anti-example.
So what about?
Greedy vertex cover anti-example. So there is one node that connected with 99 vertex. Yeah, like this picture. And if we first look for this, so there was examples that we cannot just search for only the one.
It was about approximation algorithms, what I say. So the question is, so an approximation algorithm say, let's just a heuristic algorithm. Let's guess vertex cover. And then see how good our guess is. It's idea of approximation algorithm. And there was, let's build vertex cover by iteratively pick the node of largest degree. And then we prove it's bad algorithm. Here we think about exact algorithm. Our answer must produce exact answer, but we are ready to wait for a long time if a certain input is bad. So if k is big, we are ready to wait a long time. But the hope is that the boss gives us a graph and asks us for small k, and then we can work with it. So we warn him, look, it's slow algorithm, but reasonable. If you give me few days to compute or you pay for some months of CPU or GPU or whatever, so I can do it for you, but k should be at most 200. So it's the deal. Yeah.
And the left branch contains the node that we picked and all the nodes that aren't its neighbors.
So the right branch, so we pick
Oh.
this node here.
And
And then in the right, yes, you're right. Yeah.
the right branches, we only remove our chosen node,
Yeah.
and on the left,
We
pick it
choose
and-
all the neighbors, yeah. And so now let us understand that this really helps, that we go from 2 to the power k. So with this algorithm, k is equal to 90, maybe it's okay. If you wait long enough, so 1 billion, 90, what do I say? Sorry, k, like 2 to the power 30, 1 second, if we program very well, or maybe 1 minute or something. So if k is 60, it's no problem. But here, it's like square root 2. It's a bit more than square root 2. That means that if k is 120, maybe you can do it. It's, yeah.
Same as the.
Yeah, because this is basically square root 2. So you can make exponent twice as big and have roughly the same time. So there is like clam value people discuss. And so state of the art is like 1.27. I don't remember. And so it means that you can make k double 1 more. Like if it's 200, you're probably okay. Well, this is theoretical algorithm. I mean, it's a very big constant in the front, and it will take forever to implement. So, but okay, so there was Chinese people for fun, they tried to push the constant. So, yeah. So to the power k. And yeah. So just many cases, big kernel. And then also the branching algorithm. Okay. Let's so now let us verify. So how do I get this number? So how did we verify the size? And so here we need to bound the size of recursion tree with something better than 2 to the power k. And so we will make a guess, and we will say that when we give a value of k, worst case size of recursion tree will be alpha to the power k. So -1. I will add -1 because when we have 2 branches, and it helps if I add -1. And so we will guess. So the size, so number of nodes, size of k, we guess it's alpha -1 to the power k. So before we had alpha equal to 2. Okay, sorry, let's say k plus 1 minus 1. And so if k equals 1, there is just 1 node. And we had alpha equal to 2, and then exponential decrease. And now let us make a recursive formula. As k plus 1 is bounded by 1, so the node that we are in, and then sk plus sk minus 3. Okay, there is an important thing I forgot to tell. So what we do another rule. If all the nodes have degree 2, then we can say the answer directly. So I changed algorithm. So we do branching algorithm, but we stop with branching if all the nodes have degree at most 2. Because then if degree at most 2 means that we have union of paths and cycles. And for every path separately, we know minimal vertex cover. Length divided by 2 rounded down. For cycle, it's length divided by 2 rounded up. So if we have triangle, we need 2 nodes. And so we have just disjoint union of path and cycle. So we add up the values for all of them and we check with the value of k, we get the answer straight away. So it means that if we decide to continue branching, there is always a node with at least 3. And so if we pick node with largest degree, then it means that in one branch, k decreases by 1, and in the other branch, k decreases by 3, or better. So this is our recursive relation. So now algorithm is clear, right? You need to say something. I explained everything from algorithm. And so we pick any node, we pick node with large maximal degree, remove it in one branch, remove all neighbors in other branch. And when we see all nodes have degree at most 2, then we finish. Okay, so size of recursion tree. When we give it value k plus 1, it will be, so how many nodes in recursion tree? We will have the root plus the size of the 2 branches. So this is s of k plus s of k minus 3, maybe s k minus 5. But in the worst case, note that if k grows, size is larger. In worst case, we have a k minus 3. And so now let us plug in solution. So we want to know the best value of alpha that respect this equation. And so here we will have alpha to the power k plus 2 minus 1 smaller than 1 plus alpha k plus 1 minus 1 plus alpha k minus 2 minus 1. And so now all the minus 1s, they cancel. And so we have minus 1 in this one. That's why I did minus 1 here. So we have nice formula. And now I can also divide by alpha to k minus 2. So what do we have here? We need that alpha to the power 3 is smaller than alpha. So I divide by k minus 2. Okay, sorry. That should be k minus 1, I guess. So I increased by 1. Oh no. Okay, so we have alpha to the power 4 plus 1. So when I simplify, so I divide by k minus 2. And so now we can see what is the best alpha if we have equality here. So it's just polynomial equation. And so we know it has several roots and it has one positive root. I forgot why one positive. I should look carefully. And anyway, we see one positive root and it's this value. Or 4, 5, 4, 6. And you were supposed to know this for exam previous time. Okay, but importantly, you know now. So what Chinese people did to get better result here, they made special cases for if all the nodes are of degree 3. So that if the smallest degree is 3, they could do something special that saved a lot of time. So they can in the 3 always assume degree 4. And actually, if there is no node of degree 5, they can do other special things. And so basically the branching is with lose 1 node or lose 5, drop k by 1 or k by 5 in most typical cases. So, and if it only drops by 4, then they analyze the 3 below it and see that there is huge drop below. So that's okay, but it's not so important. Okay, so now we understand the definition of P. We repeat what is branching. Now let us think what is kernel again. So idea of kernel, and it's a very important idea, and people don't think about it in industry. They don't know about it. And there are a lot of clever ideas to make your problem smaller and then solve it.
Yeah.
So for vertex cover, let's think about our problem. So formal definition is that you do polynomial amount of work and end up with a problem that has different value, whose size only depend on k. So vertex covered problem, it can be solved, has kernel. So you reduce problem, and after reduction, its size is bounded by some function of k, and hopefully polynomial and k. And that means that you start with very big graph, you shrink it, and you only need to do brute search on this very tiny graph. So that's idea. So that is so there is a theorem that says vertex cover has kernel of size k squared plus k. And this we also studied last time. So if I forget to say what is the parameter, it's always natural parameter k. Vertex problem has kernel size k. And so we have certain reduction rules. So when we solve vertex covered problem and our graph has isolated node, what should we do with it?
Should do with it because
it doesn't matter. We need to cover the edges, so it doesn't change the problem. So it's easy reduction rule. So I make scissors here. Drop isolated nodes. And so we will make silly rules, and altogether they're amazing. So that's what not knowing in company. Just do all the stupid things, and then you have, and let them work together. So do it iteratively. So second thing, what if node, it is a small degree. What if node has very big degree, has a degree more than k? What should we do?
we need to edit.
Yeah, we need to take it in the vertex cover.
And do it with the edges.
Yeah. Why? What happens if we don't take this node of degree k plus 1, if we don't take it in the vertex cover?
We might not find the correct solution.
We need to add all your neighbors.
Yeah, we need to cover the k plus 1 edges, but we decide not to take the node. So that means all the neighbors have to be taken, but there are more than k of them. So then the answer is no. So no point in checking this solution. So second step, if node has degree more than k, strictly more than k, then delete it and we replace k by k minus 1. And so we take it in the solution. That means that we have only k minus 1 nodes for a vertex cover left. Okay.
We also can see for the pairs of the nodes. So
you mean nodes of degree 2?
No, if there one edge with 2 nodes.
So what do you mean? So an edge? Yeah. If this, we can also drop it. Yeah, good plan. Yeah. So definitely do it. Isolated edge. And so k by 1 and drop the edge. So, but I want to think you about this. There are more like this. If you have node of degree 1, what should you do? And so if we have graph like this, and then so here is more. So you have node of degree 1, what could you do?
Add the neighbor.
Yeah. This goes in the vertex cover because no point of putting this node in the vertex cover to cover this edge. It can only help if you choose this one because these two are also covered. So this is more. So it's for programming exercise. I'm helping too much now, but it's okay. Yeah, good idea. Okay, so but now let's think about these two rules together and we apply them until we can no longer apply them. And then if we can no longer apply them, we do the following. So if graph has more than, so if we have more than k squared plus k nodes, answer no. It's really cool. And so if we apply this and can no longer do it, we check if we have more than k squared node. If so, we say no. And otherwise, we end up with a graph that has at most k squared plus k nodes. And so if we run this procedure, and so I will prove that no harm in applying this rule. Answer doesn't change. And after I apply this, we have an algorithm that shrinks maybe very big graph, either produce answer or gives very small small graph. Okay, why is this rule correct? Somebody remembers it. We explained it in one but last lecture. So let's say contrapositive. They say if n is large, then answer is no. I will prove contrapositive. That means if answer is yes, then n is small. So lemma, if vertex cover of size k exists, then graph has at most k squared plus k nodes. Okay, let's just draw the graph. Where is it? Cleaner? So I will draw vertex cover first. So blue nodes, they are the vertex cover. And remember what I said, we apply this rule until it was no longer possible. That means no isolated nodes and all the nodes have degree at most k. So if the blue nodes are in the vertex cover, so at most k of them. Now let's think how many edges can there be? So we know every edge has endpoint on the vertex cover. So we can have at most k edges on every node because this rule cannot be applied. At most k, and the same here at most k.
And also k edges between?
Yeah, there can be edges between, but doesn't matter. At most k squared edges, and they must all on the blue node of vertex cover. Okay, so how many? We know that all nodes have degree at least 1. Where can be the other nodes? They must lay on one of these k squared edges. So they must be on these other endpoints. So what's maximal number of nodes we can have? It's size of vertex cover plus number of edges. Because every node will use one of these edges. And so we have at most k squared nodes here. At most k squared black nodes. So in total sum, at most k squared plus k nodes. So if vertex cover exists, at most k squared plus k nodes. Okay, so this is kernel for vertex cover. So here I explain. So now we can combine kernel and branching. And so before we had 1.4645 to the power k, and then it was n squared work in RAM model, like in your algorithms. So what did you have to do? Find maximal degree of node, well, even n. So you iterate over all the nodes, and then just store the maximal degree always. So in the beginning you compute it, okay, and then so in the beginning you do some to make some data structure, whatever. So this will be the runtime. So now it's better with kernel because we can directly decrease to k squared size. So we have the same thing, but now multiplied by k squared, but here we, yeah, probably on. I think it's this time to evaluate kernel. I'm not sure, maybe n cube, but it doesn't matter because this is exponential. If this is your bottleneck, you're very happy. Yeah. Yeah. So it's improvement. Okay. So now, so that we can combine branching and kernel. And so people think about what is smallest kernel. And there is lower bound on the number of edges. So, okay, let me first speak about, so we can do better than k squared size of kernel. We can have linear size of kernel. We can have not k squared, but kernel of 2k. Oh, sorry, that should be k squared. So that's what we proved. And now we do better, not k squared plus k, but we will have 2k. And this follows from linear programming reduction. So it's important technique for solvers. It's how to reduce our problem to linear programming relaxation. So let us first have to relax to linear programming. Let us make first a binary variable. So imagine that we want to know whether this graph has a vertex cover of size 3. So how can we code a vertex cover with numbers? We just make a list of binary numbers for every node. So there will be XA. So let us give the nodes a name, A, B, C, D, and E. And so we can make this. So there exists a binary integer binary programming thing. So that means that you can ask for linear equations on binary variables and ask solver if it has a solution. So there is also integer programming. Maybe you heard about this. So so there is solvers, Google XOR solver and SAT and so on. And famous solver is integer programming solver. You give it a system of linear equations and it tells you whether it has solution where all the numbers are integers. And then there are variants like binary programming where you ask, are there solutions, set of linear equations? Are there solutions with value 0 or 1? So let's do binary programming. It's rare. Usually integer programming exists and very famous mixed integer programming. So where you said, I get linear system of equations, some variables should be integer, other can be floating point. It's huge business. So you should learn about this. And all these NP-complete problems, you can give them to such solvers. But such solvers do solve pretty difficult problem. So for every node, we will have a binary variable xa, xb, and so there are values in 0 and 1, and we can give the solver linear equations. So the idea is that xa equals 1 means that we take A in the vertex cover. Xe equals 0 means node E is not in the vertex cover. And so we can code a valid vertex cover as a set of linear constraints. And so here we go further, E goes to Xe. And so we need that every edge has one endpoint in the vertex cover. So if we think about this edge, we need that Xe plus Xa is at least 1. And so here, linear inequality. Oh, did I say system of linear equalities or inequalities? Anyway, these things, they want inequalities. And they check whether there is integer solution. Or we think about binary solution. So then I don't need to, I mean, this special case of integer solution because you can add constraints that xb is, or xa is between 0 and 1. And so if you need integer solution, it forces binary solution. Okay, and this we do for all the edges. So xe plus xd should be equal to 1 and so on. And then we ask solver for solution. So it's overkill for vertex cover, but for other programs, people actually do this. So I once did a project with Huawei company, and that's how they find routing for between big servers to distribute capacity. Well, okay. The algorithm they have to deploy is on small chips. They cannot run solver, but for research, they do it like this to check it. Okay. So now, after we write down all these inequalities, we should understand it has solution if and only if vertex cover exists. So the input will also be a number, and we need to require that the size is at most 3 of the vertex cover. So that means xa plus xb plus and so on plus xe is bounded by 3. So this is one more inequality. And now we have that vertex cover of size 3 exists if and only if this system has a solution where all variables are integers, binary. So why? Okay. If vertex cover exists, then we set the variables appropriately. So those nodes in the cover, they get 1, others get 0. And then we see that all constraints must be satisfied. The last one because the size is 3, and vice versa. If there is a solution, then we set the corresponding nodes. We put them, all the nodes with variables 1, we put them in the vertex cover. This guarantees there are at most 3 in the vertex cover. And these constraints make sure every edge is covered. So just by construction, it's equivalent. Okay, but integer solver, for integer programming, you can give it and it can think forever if he finds that task too difficult. It's NP complete, like we can break crypto by making reduction. So we can, getting the password, we translate to SAT and then SAT to, with all the reductions we learned in previous semester. And so if solver always works, we can break crypto and nobody succeeded to this. So that means that it can happen in practice. Solver runs for days and without answer. But there is other thing we can do. Instead of asking for integer solution, let's ask for fractional solution. Let's allow rational numbers. And then we know that in theory, programs should work in polynomial time. Okay, in practice doesn't work, but in theory it should work. So there is some. So in practice you can, if not too big, if k is smaller than 100 nodes, it works. So, but let's say it works more often in practice than integer programming solver works. But now we can have, so what we can do is we can optimize, so it needs to give it a target and say minimize this sum. And it will give you a minimal value of linear function under linear constraint. But it will give you a solution that is fractional. So for example, if we give it a triangle, and we want a vertex, so we give the system for triangle. From vertex cover, it means that it will, let's call it y, ya, yb, and yc. And so it will find the solution. If we want minimal size fractional vertex cover, it will assign 1/2 to each of the nodes. We want the minimal sum of ya plus yb plus yc, such that ya plus yb is at least 1, yb plus yc at least 1, and ya plus yc at least 1. So this is just an example. So when we ask for linear programming to give fractional solution, we will get a value that should be higher than the size of fractional solution. Lower. So we ask the minimal one, we ask for minimal value. Like in the triangle, here we get a sum 1.5, while minimal vertex cover is 2. And so if we look at fractional relaxation of this problem, we can get smaller value. But imagine that the value we get is still bigger than the k which we started. Then we know there exists no solution. Right? Because we ask for more general type of solution. So it will give us theoretically guaranteed a value in polynomial time that might be smaller. But if this smaller value is already bigger than our bound, then we know that with integer programming, no point to run it. That means no point to run an algorithm here. Okay, so that's the plan. So now let's return, how does this connect to creating a kernel? So it turns out that we make a fourth rule. It was invented by Nemhaus and Trotter in the 70s, long before people thought about kernels. Rule is very simple. You ask for fractional solution, and then it will answer. It will say 0.6, 0.3, 0.5, and so on. And the rule is drop all nodes bigger than drop all nodes different from 0.5 is the rule for the graph. So all solutions not 0.5, you drop them. And you decrease k by number of nodes strictly more than 0.5. So this is very powerful rule. Okay, so after we apply this rule, and so drop nodes A with xa not equal to 1/2, and A goes to A minus number of nodes with xa bigger than 1, strictly bigger than 1/2. Okay, and now I claim that after we apply this rule, so then we repeat everything. So we can repeat this rule until all nodes have value xa equal to 1/2. And then we know that the number of nodes must be at most 2k. And so we have obtained this problem. So if nodes is more than if number of nodes is more than 2k, what does it mean? We have, so after we iteratively apply this rule, all the nodes will have xa equal to 1/2 because we throw away them. But now linear programming node bound, so fractional bound is half of the nodes. So if k is smaller than half of the nodes, we can directly say no. So it should actually be added. So if k smaller than number of nodes n divided by 2, say no. Okay, this is a bit tricky here, but n I knew that mean the new n. Okay, so at first I still need to prove why we can drop all these nodes. But after this is done, do you understand why we can do this? Let's make a new rule here. So, but no, this rule can only be applied if this rule can no longer be applied. With this, so we apply it until all the nodes have xa equal to 2. So and then our algorithm gives this, and then we can apply this rule. So it's clear, right? If k is too small, we drop it. And so if we cannot apply this rule, it means that number of nodes left is at most 2k. So this is algorithm. But now we have to prove that this rule is correct. Yeah. Okay, so people are tired. But it's normal because it's 1.5 hours. So, okay, I will explain why this rule is correct next lecture.
Next lecture or next seminar, like in 2
Yeah. So there will seminar now, but next week I will explain. Yeah. So why this rule is full result. So then we continue. So I will skip this. It was optional, and then next lecture I do the new things. So we did almost everything. So I just need to. So we almost finished with this thing. And then, so there is algorithm. I will write it in the lecture notes. And if we decide to use this, so problem with linear programming is that in many practical cases, so theoretically, it's really powerful rule. Like you run it, you drop it. The problem shrinks very big. You think, wow, cool. But then if you run branching algorithm afterwards, it takes more time for some reason. I don't know why. And so I will check this rule on the data set. If it doesn't work, I will warn you that you don't need to bother with it. So yeah, I still need to start programming, and I want to extend with more cool rules. So let me say something, so non-technical things. So the question is, can we do better than linear kernel? Like shrink the kernel more than linear? And answer is, if you can shrink to k1 minus epsilon, k times 1 minus epsilon, it violates exponential time hypothesis. So people have proven this. So if you have this, sorry, it's not right. It's k to the power 1 minus epsilon. And so if there is a kernel of size sublinear in k for some epsilon bigger than 0, it would contradict exponential time hypothesis. No. Okay. And so also another problem, kernel has many edges. So there is another result that says that the number of edges is less than 2 minus epsilon. Then some other conjecture and computational complexity fails. So it is called collapse of time hierarchy, collapse of polynomial time hierarchy. So it's proven by Van Malkebeek, who is also from Belgium, but okay, yeah. And Dal, okay. And also Fortno and Santanam, and so on. So much better than 2 to the power k is not possible. But there exists algorithm that says you can reduce to kernel of size c log k for every c you want. But if you choose c big, then so kernel is algorithm that runs in polynomial time in n. So just polynomial, regardless of value of parameter. But this algorithm runs in time to the power O of c. So if you choose c, any constant you want, you can drop the size of the kernel. But your kernel algorithm becomes slow. So this is algorithm by Lampis. And so it can be quite significant. But it's actually, as I understand it, something like 2c. It's the power. So that means that you can just get rid of a bunch of branches. So you can make your branching tree. The size is exponential in k. So you might want to pay this for this decrease. So you can actually pay for a big c, sorry, k to the power 2c. So maybe you want to make this very big to make your search tree smaller. Maybe you want to spend half of the time of your total search to decrease the size. And then if c is equal to 4 or something, then this can be significant. Like in the programming exercise, k will be 80, and you have 1 minute for these examples. Well, now I move to C++, it should be even better, like 90, I don't know, it's like 1,000 times faster than Python. So it may be k90. So, but then log k is also significant, like more than 6, 7. So if we choose c equal 4, it's already a big reduction in the size. Okay, I will see it, but the Lampis algorithm, no chance you can program this, so I need to program it. But since I don't know C++, I'm for sure I will fail in a few days. So I think you're good this year for this Lampis algorithm. Okay. Yes, so let's have 10 minutes break. Then we will go to seminar. And so in seminar, there will be one more reduction rule for vertex cover that we didn't discuss yet. Oh, by the way, node ones were in previous homework. So, okay, doesn't matter. So one more, so it will be notes for degree 2 is exercise for the seminar. But the other things is just to train for seeing reduction rules. So it hurts on the brain to find reduction rules, but you can get, so some people ask me, write some program that does some routing, and then I gave them reduction rules and they paid 9 million to the university for, it was not so difficult. But in the all of the company, they say, no, we're sure you will fail. So they say, like, write a program that can do brute force search in certain time. So I got 1 second. It's not much on 11 cores. No, well, to be precise, so there are 2 variants. One variant we got 5 seconds on 11 cores, And then we used 1.3 seconds on one core. So it was like way better than, and they believed it was a trap. We couldn't do it in 5 seconds with 11 cores. But to see the reduction rules, you need to train. And they say, what parameterized complex? We don't know this, so don't use it, they say. Because it's impossible that we don't know something useful. No, I mean, I'm simplifying. It was just important part of solution. So there were more things needed. So it was a big work, but they were very happy. Okay. So
Can I ask you about the
yes.
deadline? So the next week will be, so in 2 weeks we have deadline for our diploma work. So
Yeah. You should work on your diploma work. And I said many times, so the deadline is 31st of March. So it's at the end of the session.
yeah, so we need to send like a program, or we need
There will be grader. So it's so you somehow give it to the grader and it replies in 2 or 3 minutes.
um,
Yeah.
yeah, so it will automatically check.
Yeah. It gives 100 tasks and then in the middle it will stop. So it will do on small examples and give you very little time. So it starts with 25 examples and you get 1 second, because then people can submit as many times as they want. And then I do the real check and it takes like 2 minutes. But you need to be first fast. So there is 1 minute to check 50 example. I will see. I need to change everything for C++ now. The
I think you can like add the poll to the Telegram, because
yeah.
I think that only one person asked you about C++ program.
No, but there was like 10 thumbs up or something.
Yeah, but I don't know if you need to
Or maybe-
spend a lot of time for it.
Yeah, I mean, I think we will manage to do it in
Yeah.
Python.
Okay,
It's
but then I
definitely simpler
can
than-
start it now. Yeah. Then I can just switch it on. And then, yeah.
Because yeah, you need to spend a lot of time for it, and every student knows the Python.
Yeah, so is somebody here who doesn't know Python? Yeah. It's nowadays all children. I tell my children Python, but I use C++ only for a short time, 20 years ago when I was like you. So, but since then, I never needed it. So,
Yeah, so maybe you can.
yeah,
leave a
by the way,
message.
we beat the company mostly in Python. So only part had to go to C++. So, yeah.
You can ask students in the group chat.
Yeah. Yeah. So those, but it should be the same for everyone. Like I cannot, like some people, if grader is not tuned properly, probably it will not be tuned correctly in C++, because I need to do it fast and it's difficult for me. And so, yeah, it would be huge help because I'm under a lot of time. Then I can just switch it on and you can start. It's by email. It's a bit slow. I feel a bit funny, but okay. It's yeah. So that's at 7:50. Let's do 7. Sorry, I forgot to give you the task. Well, if you plan to stay.
Yeah.
No, anyway, you can have the task. Sorry. Mhm.